Okay, so let's recall that in the previous video we ended with this definition, the definition of a cyclic space with respect to a nilpotent operator. So before we do anything else, let's just once again see the definition. So you have a nilpotent operator T on a finite dimensional vector space V, a subspace M of V whose dimension is small m and that is also invariant under T. That means M is invariant under T will be called a cyclic subspace with respect to T if the following two conditions are satisfied. What are those conditions? The image of the subspace M under the mth power of T to the power m is the zero space. But the image of m under T to the power m minus 1 is not the zero space. That is condition 1. And condition 2 says that there exists a vector z in M such that these images of z under the successive higher powers of T, they form a basis of M. Now what is the next result about this type of cyclic subspaces? If M is cyclic with respect to T and again is of dimension M, then the dimension of M T to the power K, the dimension of the image of M under the kth power of T is M minus K for all integers K less than or equal to M, non-negative integers of course. So let's now see the proof of this. So in the proof we are, in the beginning itself we will handle one trivial case, namely the case where K is equal to M. If K is equal to M, then M T to the power K is just M T to the power M. And by condition 1 from our above definition, this is the zero space. So in this case, the dimension of M T to the power K is the dimension of the zero space, which is 0, and that is also of course equal to M minus K, because K and M are the same in this case. There are some little things about which we sometimes get confused. Do you remember why the dimension of the zero space is 0? Sometimes this is taken as a convention, but actually it can be simply thought of just like how we think of dimensions of vector spaces. What is the basis of the zero space? The basis of the zero space is the empty set. You may think of the singleton set consisting of the zero vector. This set spans the zero space, of course. However, it is not linearly independent because of the presence of the zero vector. This is linearly independent and it also spans the zero space. This is where the confusion may lie. How can the empty set span the zero space? About which I am not going to say anything more right now because we are doing something else. If you do not remember how that is the case, you try to think of it, or you go back to your dimension theory and see there how it is that the empty set spans the zero space. And that may open up something about which you may not have thought really deeply. Maybe the definition of span that you are using really does not take into account this case. Maybe you need to see the slightly more general definition. Okay, so I will leave it at that and let's come back to our proof now. Okay, so this case has been handled, so now we can assume that k is less than n. Assume that k is less than n. We have already used condition 1 in this case, now we are going to use condition 2. There exists so we are going to write that same thing verbatim. There exists a vector z in M such that these vectors form a basis of M. But we are not exactly interested in M, we are interested in mt to the power k. So let's see what happens if we apply that kth power of t to each basis vector here. So I am straight away going to write this. Hence, the vectors k plus, or perhaps I should first write m minus 1 and then add k to that. These vectors span mt to the power k. Do you see how? It's very easy, but still let's see the details. Because these vectors span M, so that's not how I should start. I should start by taking any vector here in mt to the power k. How will that vector look? It will look like this. Should not write small m because that's already dimension. So let's just write u. That's how a general vector in this image is going to look like, where u belongs to M. Now u belongs to M and these vectors form a basis of M, so u will be a linear combination of these vectors, and that's why u will look like this: alpha 1 z t plus alpha m minus 1 z t to the power m minus 1 for some scalars alpha I. Now, using the fact that t to the power k after all is a linear transformation, so applying all the axioms and everything, ultimately you get this. So that's how any element here is a linear combination of these vectors, and that's why these vectors span this image. But now you also use the fact that the mth power of t, that is t to the power m, when applied to any element of m gives you 0, because m t to the power m equals the 0 space. That is, although here you are seeing powers of t potentially exceeding m minus 1, because you have you are adding things, right? In fact, here you see m minus 1 plus k. But some of the later vectors actually are 0. So that, in fact, let's write the reason. Since m t to the power m is 0, the vectors set t to the power k, t to the power k plus 1, and so on, t to the power m minus 1. They also will generate, means will span m t to the power k, because the other vectors that may come after this term are all 0. Okay, so they also span this. Alright. So you see that because of this slightly reduced set means possibly we do not have the other terms which come after this. Because of this reduction, whatever vectors we end up getting now actually form a subset of the previous basis of M, which had all those vectors z, z, t and so on up to z t to the power m minus 1. This now becomes a subset of that. Also, and that is why, because that basis is linearly independent, so this subset is also linearly independent. This is a subset of this. So, the vectors are also linearly independent. So that's it. We have proved that they span this image mt to the power k and are also linearly independent. So they form a basis of mt to the power k. Also, linearly independent. So, they form a basis of m t to the power k. So now the dimension of m t to the power k will be the number of vectors in this basis. Thus, Now, how many vectors are present here? If you start your counting from here, because you see the 1 here, no? Then what do you get? See, if you start your counting like this, you have k plus 1 here, so this is the first element. Not considering this one, of course, we will do that afterwards. So this is the first element. The next element will be z t to the power k plus 2. So that 2 corresponds to the second position of that element. So what will be the position of this element? You have to express this m minus 1 as k plus something, because then only it will fall under that counting scheme. Now m minus 1 is k plus m minus k minus 1. We have added a k to compensate for that, we have to subtract k as well. That means the last element in that counting scheme becomes the m minus k minus 1 position element. That's why starting from this second element, we have this many elements till we reach this element. But now if you add the first one also, then to this you add 1 as well, and that way you get, in total there are m minus k elements in this basis for m t to the power k, and that's how the dimension of m t to the power k is m minus k. Okay, so that completes the proof of this lemma. Now this lemma will be used in the main theorem that comes next. That theorem tells us that those integers that we saw in the key theorem about nilpotent operators, those ni's, n1, n2 up to nr, which we have called invariants, really deserve to be called invariants because of this next theorem. And what this theorem says is this: two nilpotent linear operators are similar, not necessarily the same, but are similar. Similarity is, in the world of operators, similarity is almost like being the same thing. Okay, just like isomorphism or being isomorphic is the same for two algebraic structures, is something like that. Two nilpotent linear operators are similar, of course, over the same vector space, are similar if and only if they have the same invariants. The invariants are same, or more specifically, the set of invariants, that's the same for both of them. If and only if they have the same invariants. It can also be rephrased slightly differently by saying that a given set of integers, like those ni's, determine a linear operator uniquely up to the equivalence relations similarity. It gives you a linear operator, nilpotent of course, but then it simultaneously also gives us all the nilpotent operators that are similar to that one. Essentially, it determines a similarity class of nilpotent operators. The proof, however, we won't go through today, that we will start. Start means we may not be able to see the full proof in the next video on linear algebra. but we will start it in the next video. So let me just end things here itself. And what do we have tomorrow? Analysis. Have we, I forgot everything. Have we already started solving exercises? Have we finished that exercise that I don't remember? I am having some very negative thoughts today, some homicidal, suicidal thoughts. Okay, so I need to calm myself down. So let's just end it here itself. So see you tomorrow with whatever it is. Until then, this is me, Lucifer from a mathematical room. Have a nice night.